Right now, data centers are burning through over 200 terawatt hours of power every single year to run modern AI workloads. This animated diagram illustrates why. The vast majority of that energy isn't actually spent calculating, it's lost in transit. Traditional processors suffer from the von Neumann memory wall, a physical bottleneck where moving data back and forth between the processor and the memory bank drains massive amounts of power. Because of this architectural wall, we cannot physically scale AI out of the data center using conventional microchips. The thermal limits and battery constraints are simply too strict. To push artificial intelligence into the physical world, the hardware itself has to change. This line graph maps out the tech industry's response to that bottleneck. According to a new market forecast, the global neuromorphic computing market is projected to scale from $8.3 billion in 2026 all the way up to $35.2 billion by 2033. What stands out on this trajectory is the slope itself, an aggressive 23.1% annual growth rate. That pace of capital injection tells us companies are racing to solve the energy crisis. The capital is flowing directly into neuromorphic computing, processors that abandon traditional layouts and instead physically mimic the neural architecture of the human brain. This growth projection isn't just an investment metric. It is a roadmap toward a new tier of hardware designed specifically for a world of decentralized, low-power intelligence. A standard microchip processes data in continuous, rigid frames. It draws power constantly, whether it's actively analyzing a complex image or just staring at a blank wall. The traditional chip on the left burns energy constantly, while the neuromorphic architecture on the right uses asynchronous, spike-based signals. Like biological neurons, these pathways stay dormant, activating only for specific events. The resulting efficiency is immense, demonstrating 60 times lower energy consumption per inference. By doing the math in memory and eliminating continuous data transfers, these brain-inspired chips bypass the von Neumann bottleneck entirely. Because these chips require a fraction of the power, AI inference can finally leave massive servers. Today, over 55% of the neuromorphic market is dedicated to edge deployment, meaning the processing happens locally, directly on the device. Consumer electronics lead this migration at 40%. Devices like VR headsets require complex, real-time visual processing, but are constrained by small, lightweight batteries. Then there's the automotive sector, the fastest-growing industry for neuromorphic tech. Autonomous driving systems need ultra-low latency perception to make split-second decisions safely at highway speeds. Similarly, industrial drones require real-time sensor fusion, combining multiple data streams instantly to navigate unpredictable physical environments with sub-millisecond reaction times. A self-driving car or an industrial drone cannot afford to wait for data to travel to a cloud server and back. Neuromorphic edge processors give them the local, instant intelligence required to operate safely. Transitioning a multi-billion-dollar hardware ecosystem carries massive financial risk, but private companies aren't footing the bill alone. Global governments are aggressively subsidizing the research. North America currently controls 38% of the market. This position is supported by federal policy, notably the $52.7 billion CHIPS and Science Act, which directs massive funding toward next-generation semiconductor research. The European Union is driving similar innovation through its Horizon funding programs, while the Asia-Pacific region is expanding at a 28.1% growth rate, fueled by national AI chip strategies in countries like China and India. By treating neuromorphic computing as a matter of national security and economic priority, state governments are covering the early-stage research costs and virtually guaranteeing a market for the hardware. There are still physical constraints holding back mass adoption. Manufacturing these chips require nanoscale precision and entirely new materials, like phase-change memory, which are incredibly difficult to fabricate in commercial volumes. And even if a company secures the hardware, they face a steep learning curve. The standard tools developers use for GPUs don't work here. Engineers have to learn entirely new spike timing-dependent programming models. This chart illustrates how the industry is solving that problem. Software is the fastest-growing component in the neuromorphic sector as organizations rush to build simulation tools. Creating these developer-friendly frameworks is the final hurdle to move this technology into mainstream commercial adoption. Ultimately, the shift toward neuromorphic systems represents a strategic pivot away from brute force processing. signaling the emergence of an efficient, brain-inspired future for artificial intelligence.